Okay, we're gonna get started here talking about some practical robot concepts, and at the end, if we have time, we'll define a user frame. This will be about 20 minutes. Let's start out here by putting the robot in the zero joint configuration. Come on. There you go. Alright. Some call this the Fanuc salute. Hats off to Fanuc, by the way, for this magnificent trainer. I really like the setup and the open space here. Alright. Here. Looking at joint 6. Use your right hand. Curl up like this. And it's going to tell you the counterclockwise direction. And we're going to talk about the counterclockwise direction being the positive direction. Because you've got the 12 joint buttons here for jogging on the eye pendant, and they all have a positive or negative direction. So what you do is, look at this. See, clockwise is the negative direction, counterclockwise is the positive direction. So in this instance, you line up your thumb looking towards you, your direction, the axis that you're interested in. So axis 6, counterclockwise is the positive direction, looking at from behind the faceplate or the flange. For joint 5 and 3, there's an X, and that means from that direction, using the right hand rule, pointing out from the X, counterclockwise is the positive direction. For joint 2, it's in this side here, where counterclockwise is the positive direction. For joint 4, similar to joint 6, you look from behind, counterclockwise would be then the positive direction. And for joint 1, you look straight down, see? Counterclockwise is the positive direction. That way, when you're jogging in joint mode, you can turn the direction you want to the first time around. Now, I want to mention something here about this posture of the robot. When joint 5 is very close to 0 degrees, or right at 0 degrees, joint angle, what you get is joint 6 and joint 4 are collinear at that point. They line up. And think of it like this. When that happens, joint 6, if we rotate joint 6 let's say clockwise 10 degrees, we can counter that with joint 4 running 10 degrees the other direction. So no matter, there's infinite possibilities here. And that, keeping the TCP here orientation, the TCP orientation will remain constant. No matter how many degrees joint 6 goes one way, joint 4 can counter it by the same amount of degrees going the other way. And when that happens, you get a phenomenon known as singularity. And, well, the robot doesn't like infinite possibilities, so it gets into singularity. And for the most part, Fanuc can overcome that. You will notice that when you're cycling through your coordinate button here for the different frames, for instance, you got the world frame, the tool frame, the user frame, the jog frame, they have an S in front of them with a slash. That stands for singularity. That means that you can get your way through the singularity while jogging. You will notice that it's usually the rotation in joint 4. It will slow down quite drastically. It may even speed up at times while it's trying to go for the singularity. So the velocity of the joint will be affected. Alright. What we're going to talk about next is the configuration of the robot. We have the flip and non-flip. We'll start with that. We're going to put the robot here in a flip position. Now, pay attention to the orientation of the TCP. Right, you got your X, Z, Y. Now, this is in the flip. I'm going to bring it to non-flip next. You see? When you go between flip and non-flip, joint 4 is going to do a full 180. As far as I know, it does it every time. Now, keep in mind when you do these configuration changes, it needs to be in joint mode. In the joint, when you tell the robot to go to the other configuration change, it has to be a joint movement, not a linear movement. If it's a linear movement, it will not do it. All right. Now, the next one is the up and down. Right now it's in the up position, and we're going to bring it to the down position here. What you notice is, again, the TCP maintains the same position and orientation, but now the robot is postured differently. And this makes sense, right? Down, the joint 3 is the one that has changed quite considerably here. And the next one here, oh, I forgot to mention here, the next one will be front and back here. But going back here to the flip and non-flip, that time when I did that flip to non-flip, see, it would be this configuration to this one. Now, over here, we have the turn numbers. The first one is joint 1, the second is joint 4, and the last is joint 6. But to be able to do the flip to non-flip, joint 6, you have to rotate considerably to the point that the turn number had to change from a 1 to a 0. And if I didn't manually put that in there, the robot would not have made the configuration change from flip to non-flip. Now 0 is degrees between what, negative 179 and positive 179. Anything less than 179, anything less than negative 179 degrees goes to the negative 1 turn number. Anything above positive 179 degrees goes to the 1 turn number. And that has to do with the joint degrees, like what this shows. Now I'm showing here up to 539 degrees, but this robot can't do that much. The joint 6 does the most rotation from positive to negative 360, so it stops here. Alright, next we're going to do the front and back posture here. Let's go down here, reset. Yep. Now for this one, joint 1 is always going to make a full 180 when it goes between front and back or vice versa. I had to position the robot facing this way. That way joint 1 could do the full 180, because the joint 1 cannot do a full 360, and it won't be able to do this full 180 if the robot's anywhere like up to the front here. Anyhow, you're going to notice here, it's going to do the flip, the front to back. I added this middle position so that it would be able to do the configuration without striking the back here, or activating the dual track safety back here. Sometimes you have to have a middle point to help guide your robot the right way, because obviously these are joint motions and they can vary widely for the robot to get to its final position. So you can see here, you got the same TCP orientation, and this will be the back. It's like, you can think of it as coming from the back or joint 1. Alright, next we're going to talk about orientations. I'm going to move this to the next position here. Oh, there we go. Reset. Alright, so this orientation business has to do with the WPR values, and this the WPR circle here. Now, W, let's get this triad here. And, okay, so the W is going to represent the rotation around the X axis of your user frame. The P is the rotation around the Y axis of the user frame, and the R is going to be the rotation around the Z axis of the user frame. All of these axes relative to your tool frame. So what you will notice is, right now, the Z's are opposite each other, facing opposite each other, and the X's are also facing opposite each other. And it so happens that this will cause the W. We'll go to the position screen here, showing the current position of the robot. I have a W of negative 180 and an R of positive 177. And yeah, so the W, remember, it's rotation around the X. Well, when I rotate the X, you see, it causes the Z. You gotta think of it like this. The Z is like the pointer for where the X rotation is. So we do a 180. So if the W, if the Z is pointing opposite, this effect is, you're going to see that in the W value. I like to call this orientation degrees instead of rotation degrees, because orientation degrees are not always rotation degrees. They're not always equivalent. And that has to do with the Euler angle calculations. It's a bit complicated. It's hard to fully grasp it, but at least we can get some practical understanding of it, unlike quaternions and other systems that other robot manufacturers use to determine orientation. Anyhow, back to this here. The W values are going to fall between 0 and 180, absolute value. P between 0 and 90, absolute value. And R between 0 and 180, absolute value. You can see here from this WPR circle, the 180, negative 180 are essentially the same point. The 0 and negative 0, they're not the same point, but they're right next to each other. So essentially the same. Very close. Now, and here, the P for this position here is 0 degrees essentially, because there was no rotation around the y-axis of the user frame relative to the tool frame. And the R, now look, the R, if we look at it, see, when you rotate the R, you're actually swinging around the X is the pointer for the R, which is the Z. And this value is what is taken into effect as to why the X's are opposite each other. So sometimes we can make use of the WPR information, make good use of it. I know somebody asked about that the other day. I mean, what's the point of understanding WPR? Having a better understanding of it. Well, in situations like this, we can gain some insights into it. For instance, like if we move to the next point here, see, all we did here was the Z here rotated. Essentially, that rotation happened around the Y axis of the user frame. And so what you see here, the P value reached 90 degrees. As you see, it was like this, and look at that. It was a rotation around the y-axis. And then if we do, for example, the next point here, what we did here, so it was like this, it was like this, and now we rotated around the X. It looks, in terms with respect to the tool frame, it's a rotation around the X-axis, but it's really around in terms of the user frame, it's around the Z. And so that's what you're going to see here. You're going to see a change here on the R value. It increased by 90 degrees. So you can pretty much tell you did a pretty much a 90-degree rotation. And yeah, because see, you're rotating it around the z-axis, the z on z in this case. It's a bit complicated, but yeah, it's worth getting a handle on this a bit. And the main values you're really looking for when you're moving with the WPRs are really the 0s, the 90s, and the 180s. As that can help tell you if you're kind of perpendicular to your frame or not in certain instances. Alright, next here, we're going to talk a little bit about tool frames, defining a tool frame. So let's go here to the next point. I'm going to get rid of this here. And let's put this one here. Okay. I'll go to the point here. And for instance, if you have to define a tool such as this, then when you put it, like for instance in this gripper can hold different types of tools. You got this here, this hooked shape tool, or this straight one that comes straight down. Since this one comes straight down, it would be best to go to the direct input here. Let's see here, we can go to the menu, frames, and there's different methods. Direct entry is what they call it. Go to the direct entry, measure the difference from the flange of axis 6 here, of joint 6. Figure out from the flange down to where you want the TCP to be. Let's say the tip here. In this case it's like 134 millimeters, and you can put it directly in for the Z value. Now, when defining the tool here, it's going to be with respect to the flange frame here. And straight out, coming straight out of the flange is the positive Z direction. That's just how it is. So if you put a Z value, it's going to be interpreted as coming straight down from the flange, right through the axis, collinear with it. If your tool is anywhere parallel with this flange axis from the servo for joint 6, if it's parallel with it in any way, you then can use the 3-point method or the direct entry if you happen to know the X spacing. In this case, I marked here on the tool, this gripper, which direction is the X direction for this flange, and it would be facing backwards. So the distance going this way would be your X value in the direct entry, and right hand rule. So you do this. So since the Z is pointing down, if X is to the back, then the Y comes out this way. So then any Y distance, you would plug it in the direct entry. Or you can use the 3-point method for that. And then you're going to have to revolve around a common point, such as from this stance. You define 3 points, approach points, typically between 90 and 180 degrees apart. So you come in, boom, 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 define it, and it will fill in the values here for the X, Y with respect to the flange frame. Alright, if you got something like this that's more complex, you're going to have to use the 6-point method. And the first 3 points is just like the 3-point method. You go around your reference stance, again between 90 and 180 degrees, you approach, and now there's going to be a 4th point. The 4th point, I recommend you keep the orientation. Oh yeah, I forgot to say that when you're doing your different approach points here, you're trying to keep that position the same and just changing the orientation.